Okay, so it's recording. Yeah, good afternoon, everybody. It's a real pleasure for me to welcome today's speaker, Dr. Karthik Raman from Tata Institute of Fundamental Research at Hyderabad. So most of you may know him. He's a young, dynamic scientist working on several research areas. So just a little bit about his academic background. So he obtained his PhD from MIT in USA in 2011. Then he was a IBM researcher, visiting research scientist, working at the IBM Research Laboratory, Armaden, from August 2011 to August 2013, so for 2 years. Then he was a Ramanujan faculty fellow between 2013 and 2015 at Solid State and Structural Chemistry Unit at IISc Bangalore. And since 2015, he is working at the DIFR Center for Interdisciplinary Sciences at Hyderabad as a reader and Ramanujan fellow. And since August 2018, he is working a reader in Center for Interdisciplinary Sciences at DIFR. And his skills, semiconductor device physics, spintronics, molecular electronics, semiconductor nanowares, interface engineering, thin film, molecular beam epitaxy, sputtering growth, lithography and nanofabrication, nanoscale device physics for next generation sensor, memory and logic applications. So he has published many high quality, high impact publications, have a few patents to his credit, has written a book chapter, and he has been recognized with several awards. For instance, the Pacific Early Career Chemistry Award in 2015, the Ramanujan Faculty Award between 2013 and 2018, Outstanding Student Award, and many.
You can leave those things.
Yeah. So with this short introduction about Karthik, I request him now to start his lecture, and I request all of you to switch off your camera and mute your microphone. And if there is any question, kindly write that in the chat window and wait till the end of the webinar. After that, we will take all the questions one by one. So Karthik, it's all belongs to you now. Please, thank you very much.
Yeah, thank you, Shubhankar. Thank you for the introduction. One second, let me just get this thing organized. Yes, thank you, Shubhankar. And I should really thank you for organizing these conference series for a long time now. It's actually a very good platform for students to really engage in and to, during this COVID time, to really be connected to science. So that's actually a good thing. I'm pretty happy that Shubhankar has taken this lead. We are also organizing this conference series for a while now, which is mostly focused on condensed matter physics. I mean, if many people are not aware of it, you could just have a look at the sessions that we are organizing at this DFR virtual conference series. But moving on to this specific talk of today. So I'm going to talk about something which is very fundamental, but very interesting, which is this concept of molecular Crane-Pulley response at magnetic surface. And if you see the schematic, that actually sums up my talk. What I'm trying to focus today is that the molecular interaction forces can be very strong when acted on a surface of a ferromagnet. It can actually pick up, or it can decouple the surface magnetism from the bulk. So one could engineer the surface magnetism and observe very interesting trends, very interesting phenomena, both at fundamental scale, but also which can perhaps one day have some relevance for technology. And that's something I'm going to stress about at the end in terms of what we have demonstrated through this molecular Crane-Pulley effect. So moving ahead, let me talk about the lab that we have where we are doing this research. So this is essentially a lab that we have built. It's focused on interconnecting different dedicated deposition systems that lets you work on multiple interesting projects especially where interfaces are the crucial aspect in the kind of work, in the kind of projects that we are completely working on. And I must thank all the funding sources, especially TFR, DAE, and SCRB research grant funding that has supported almost all our activities so far. And so in our lab, we are primarily focusing, we have primarily in fact focused our research in the last few years in 3 major topics. One is interface assisted spintronics, molecular spintronics, and that's something I'm going to talk about in greater detail in the rest of my talk. Apart from that, we are also actively working on proximity effect studies and topological insulators. Now, this is a very interesting concept where the topological insulator surface states. We know that these are systems that are insulators in the bulk, but they conduct at the surface because of the topological nature of these 3D systems. And interestingly, you form these Dirac cones at each surface, which are topologically protected by the time reversal symmetry of your system. Now, the most interesting thing is what happens when you proximatize these surface states, these Dirac states, by a ferromagnet, which doesn't destroy the topological character of the surface, but gives rise to very exotic physics. So that's something that we work on one topic, which is to proximatize these with a ferromagnet, which is an insulator. It's a ferromagnetic insulator. So europium sulfide is what we have initially right now demonstrated, which is we've grown these systems epitaxially, bismuth selenide especially to start with, on different substrates. And you can see a cross-sectional image of amorphous EUS that is grown on these bismuth selenide films, which are stacked layer by layer. And this is a work that is ongoing now. We have actually extended these studies to other 3D topological insulators. But the primary first work is already published in PG Quantum Materials, and we have more results that is part of the ongoing effort in our lab. The other is more interesting. It's a recently developed field, which is on Kagome antiferromagnets. So I have a postdoc, Joy Mukherjee, who's working on this aspect. The main interesting aspect of these systems is that they are strongly spin correlated. It's basically 2D spin lattice network, which is known to give rise to very large Berry curvature physics, and therefore can be seen from any transport, anomalous Hall transport measurements. And not just that, I mean, the band structure physics and the topology associated with these 3D materials is quite exotic. And just to give you a flavor, I mean, typically these systems are also known to show 3D Weil fermions, which basically means that if you take a 3D Dirac material with a Dirac cone, for example, in a 3-dimensional momentum space that I've shown here, it's my slide. Is my pointer working? No, right? So you can see the arrow, right, Shubhankar?
Yes, I can see it. No issue.
Perfect. So you have a Dirac point here, and the interesting fact is that when you have inherent 2D spin system in these materials,
I'm sorry to interrupt. Maybe you can use that ledger pointer. That would be clearly visible.
Yeah, that's what I'm aiming for. Yeah, is that fine? You can see.
Yes, it looks good. Please continue.
So what happens when, especially in these Kagome antiferromagnets, which inherently have a certain spin moment, you can actually create Weil fermions, which is nothing but 2 Dirac cones with different chirality, which is exemplified here on the right, where each band structure corresponds to a certain chirality of your electronic structure. And this is what gives rise to very exotic interface physics, material physics in terms of chiral anomaly, and flat band physics also is something that adds up separately in these band structures. So overall, we have an article which is available in the archive, and we have some more results ongoing in this lab. So let me now get back to our interest, which is on interface assisted molecular spintronics. That's the goal of my talk. So I've divided the talk into essentially four groups. Firstly, I want to talk about how this field has evolved over the last decade, I would say. So one of the first results came from 2009, 2010, and that's when the field evolved. And over the last 10 years, there's been a lot of interesting developments. I'm going to just glance overview of the very interesting physics that has come out of it. And then we focus on a specific aspect, which is a molecular exchange bias system, and move on to our particular result, which has emphasized on a new physics, which is a molecular Crane-Pulley effect in these monolayer exchange bias systems. So this work was done by my student Suman and Saurabh. Suman was one of the leading student who was working on this project, and this work is essentially published in this article, and most of my talk will be focused on the work that is done in this paper. So if you are interested, please feel free to read for any further insights. And lastly, I will just conclude with some future outlook in terms of what we are currently doing in spin glass response. Okay, so talking about 2009, 2010, when people were looking at interaction of molecules on surfaces, this research was mostly focused on materials like platinum, gold, and surfaces which are mostly inert. And on those surfaces, it was well known a molecule interacts with the surface is mostly Physisorption. And as a result, molecule can retain its electronic states, which are essentially shown by these isolated state systems here. Surprisingly, every time laser pointer moves out. Yeah, so they are shown by discrete electronic states. However, when they Physisorb, you can still model them in terms of renormalization theory, which will eventually give you a slight broadening of electronic states. However, most of the time, you can still model them within the perturbation limit. But things change, which was only became evident in 2010 onwards, which is the role of chemisorption. So in molecule, if you put them on a reactive surface, especially ferromagnets, which has these interesting orbitals, for example, the d orbitals, if there is a strong overlap of orbitals and exchange charge transfer through across the interface, you can actually create these hybridized states, and which is what I've shown here. So if you take your initial ferromagnet, which has been polarized bands, as you can see here, and then you have discrete molecular levels, when you bring them together and they interact, you can hybridize, and the states that you form on the right, which you can see, has no parallelism with what is there for your surface or your molecule. So you're creating new interface states, which has exotic properties that we'll study about. And it's interesting now to look at possible ways where you could control and tune these interface states. So this is a review article which I've written, and this has almost all the important aspects of what I'm talking about in the initial slides, and its relevance in spintronics. So let's move ahead. So the question that essentially arises is, when you talk about interface states, how do you model them? How do you picture them? How do you actually can experimentally demonstrate the formation of these interface states? And that's where one of the very pioneer techniques was developed by Wiesendanger in Germany, which has been polarized STM. So what you do here is, if you have a magnetic tip and you place and you scan it over a surface of iron with a molecule on top, and you can essentially plot the electron density of states of these systems. And what you observe here is a very nice image showing the molecular density of states. But more interestingly, you will see that you can map the spin contrast. You can get the spin contrast. So the green represents positive spin polarization, and the blue here represents the negative spin polarization. So you can see when you are on an iron surface, you are in a negative spin polarization. But as you scan over the molecule, you end up into a spin inversion. You end up into a state where the spin polarization is inverted. And this experiment has been done. So you can see the spin contrast density of states that is taken at different bias voltages, 1 volt, 50 millielectron volt, minus 0.2 volt, and minus 0.9 volt. And you can essentially get very different molecular orbital representations. Most strikingly, the simulation, which is from DFT calculations, which assume the strong hybridization effects, a pi d hybridization effects across the interface, you can very nicely replicate the experimental trend. And that's one of the beautiful points confirming that these interface states do indeed hybridize very strongly and giving rise to a very interesting spin character. This was one of the first works in 2010 that actually helped even us to reimagine the aspect of spintronics with molecules. And that's where we actually worked on a specific system, zinc methylphenidate, which I'm not going to talk about, but this is an article published in Nature. So the concept here was very simple. We demonstrated a nanomolecular spintronic device, which is essentially shown schematically by this device configuration, where you have cobalt bottom electrode, you have a molecule, and you have top copper electrode. Now, as you might have noted from earlier talks, maybe from this series and otherwise, when you talk about the magnet resistance signal, a GMR or a TMR effect, in all these cases, you need two ferromagnetic electrodes, one acting as spin polarizer and other as analyzer. And the relative orientation of this bottom electrode ferromagnet or ferromagnet is what decides the resistance change. Surprisingly, in our system here, just by using a single ferromagnet, you can observe a resistance change. Okay, so that's what we coined this as the interface magnet resistance effect. So and this is observed from low temperature to all the way up to around room temperature, showing 22% resistance. But the main take-home message of this results were fourfold, and this was one of the first few results that really mind-boggled many people in terms of what's really happening with molecules. So we reported for the first time that you could actually induce magnetism in the molecule, and this magnetism can be retained all the way up to room temperature. That was one of the first findings in this work. Secondly, we also demonstrated that you could actually tune the exchange coupling between the molecule and the surface. There's a strong exchange coupling which can be tuned from parallel to anti-parallel, and by external fields or by field cooling procedures. Thirdly, this is now very well known topic, which is surface magnetic anisotropy enhancement, which is also called surface magnetic hardening. And what we have demonstrated here was that by just putting the molecule on a surface of cobalt, you can harden the surface. You can increase the cohesivity of the cobalt by many folds, thereby increasing the spin-orbit coupling induced magnetocrystalline anisotropy in these surfaces. And lastly, we demonstrate spin filtering action, which is nothing but talking about when you try to inject electrons into the molecule, which is shown by the red curve here. You can see that because of its interaction with the ferromagnet, the spin up and spin down density of states here, they have different activation energies. For example, the spin down state has a lower barrier height compared to the spin up. And when we talk about injection current, the current always scales exponentially over the barrier height. And therefore, you can actually achieve more than 99% spin polarization just by having a spin filtering action in terms of difference in the barrier height of these two systems. So let's move on to some of the confirmations after our work. So we proposed the spin filtering effect, which is nothing but talking about how the spin up and spin down density of states in a molecule are spin split. They occur at different energy levels above the Fermi level. And this was shown in terbium dialysate molecule grown on the surface of cobalt, where you could see this spin band splitting. And this was a direct confirmation of our results reporting spin filtering effect. Not just that, but inducing moment in molecule or even graphene is somewhat it's a 2D molecular structure. So this is a work again that was shown that when you put graphene on a surface of cobalt, of course intercalator when I'm going through details, but if you have graphene on a surface of cobalt, and you can see that here what you're seeing again a spin contrast, where you're looking at different fragments of graphene. Okay, so some are green, some are red, some are, and then in between the green you have blue. So what you essentially see is again the same contrast, which is you're going from a positive spin polarization to a negative spin polarization in your graphene fragments. So you're essentially ending up into a scenario like you was going to a 0 state to 1 state. One could think of this as a molecular memory device. You could think of it as a graphene fragments storing information of zeros and 1 bits. And this is again a confirmation that you could induce magnetism in the molecule, or in this case, graphene. And all these gives us a lot of interesting effects in terms of potential for scalability technology, and that's something many groups in the world are trying to work at. Now, surface magnetic hardening is another interesting aspect which evolved after our first work, which is talking about enhancement in the cohesivity, which is shown here from DFT calculations, where you could see an enhancement in the cohesivity of ion PCP interface compared to just a reference ion here, where the cohesivity is much smaller. And this surface magnetic effect has now been reported on many interface systems, whether C60 molecules or TTF, ACNQ, and many others. And this is now a well-known concept that spin orbit effects across the interface and also exchange coupling. For example, in this case, they have shown that even the spin exchange coupling in the surface can be greatly modified. In some cases, can reduce by a factor of 3. In some cases, can increase by a factor of 5. And this whole thing essentially can really play an important role in tuning the surface effects. So with this, I am also looking at one more aspect, which is talking about a new form of surface magnetism. So far, our work, whatever results I had discussed by us and others, were primarily focused towards understanding interactions between molecule and a ferromagnetic surface. But this is something that I had thought about when I was writing this review article, which is it's not really required that you need to work with ferromagnetic systems. It could very well be that if you have strong interaction with a non-magnetic transition metal surface, which has enough overlap with the molecule, the hybridization can induce ferromagnetism even in non-magnetic surface. And surprisingly, within a year, we had this result from University of Leeds, who reported ferromagnetism in copper. And this is the work that they have done, where they could see that whenever the C60 molecule is directly in contact with copper here, you could observe clear hysteresis. And this is maximum at a thickness around 2.2, 2.3 nanometers of copper. As soon as you put a decoupling layer, say aluminum, between copper and C60, this effect goes away. So this is another confirmation of the strong interface hybridization effects that can actually even induce ferromagnetism in an otherwise non-magnetic material. Why does it happen? So this is something that was answered, which is when you talk about ferromagnets like iron, cobalt, and nickel, you talk about inducing or talk about ferromagnetism that is induced by band structure of these materials. And that comes from what is called the Stoner's formalism, Stoner's criteria for ferromagnetism, which essentially tells you that if the exchange integral here times the density of states at the Fermi level is greater than 1, which essentially signifies that the cost of adding an electron from, say, one spin to the other spin more than compensates the energy that is gained by the internal exchange or the correlation, then you could actually induce spontaneous ferromagnetism in the material. And that's what happens in ferromagnets like iron, cobalt, and nickel, giving rise to the spin splitting density of states. Now, same thing can happen if you have a molecular state. For example, since the molecule has discrete states and you have copper surface, which are otherwise diamagnetic, but when you hybridize, you can create new electronic states. And it can very well be that these electronic states across the Fermi level can lead to a spontaneous phase transition into weak ferromagnetism by actually creating this induced magnetization by creating a spin split density of states. And this is the effect that actually leads to ferromagnetism in copper in their reported systems. So up till now, I have essentially given you a flavor of all these various interface effects with molecules, which are otherwise really not observed in inorganic systems, I would say. I mean, this is a strong role that molecule plays in the interaction and the kind of interaction forces that it can generate at these surfaces. So now let me go ahead to the second aspect, which is the specific aspect of molecular exchange bias phenomena. And this is somewhat one of the first results came in 2015, but we were always trying to understand from different perspective. And since I was building my lab, it took a while to actually help us get started with the idea that I had in my mind since 2015. And this is something that I'll now discuss about our results. So before I move on to the aspect of molecular exchange bias phenomena, let me just give you a brief overview of what is exchange bias. If I take a ferromagnet here, okay, which has this magnetization, and I measure, say, its magnetization versus field using SQUID or VSM or some magnetization measurements, you will see a hysteresis response like this. Or you could measure resistance of this film as a function of field, and you'll see an anisotropic magnetic resistance where the dip or the peak, I'm just giving an example of a dip, but this happens around switching field of the ferromagnet. Okay, this is very well known. Now, if I put this ferromagnet in proximity to a very hard layer, magnetically hard layer, okay, and then I do the same measurement, what it does is that you will see that the ferromagnet on top its hysteresis response is shifted from the origin, and the same happens for the AMR response. So you give rise to an exchange bias shift denoted by this HEB, okay, and there'll obviously be change in coercivity as well depending on how the system performs. But the main take-home message here is that you need to be able to have interface effect to be able to create such a phenomenon. And how it is done practically almost throughout in our understanding of exchange bias systems that has gone into fundamental insights and also into technology in hard disk drives is to use a ferromagnet in proximity to an antiferromagnet. Now, when you raise the temperature to above the Néel temperature on the ferromagnet, you are in a paramagnetic state. The antiferromagnetic material is in a paramagnetic state. And so you get back the old hysteresis. But now if you cool down a system in field, which aligns these domains in ferromagnet, and then you do a measurement, this is what gives rise to exchange anisotropy across the interface, giving rise to this shift. Now, there is a fundamental problem with these systems in terms of scaling. Now, when you try to reduce the thickness of the antiferromagnet, for example, when you try to reduce the thickness of the antiferromagnet, you will observe that there's a critical thickness below which you will no longer be able to generate any exchange bias phenomena. Okay, so in that sense, there is a scaling limit to these techniques, which has limited or which may be limiting in the future when we try to build 2D spintronic devices. Now, let me come to the results on molecular systems. Now, there was a result in 2015, the first results that appeared in Nature Materials, where the focus was towards, for example, using this manganese thiazolide molecule, which people have demonstrated in the past using squared and other measurements, micrometer measurements, where XMCD actually, and showing that they could organize themselves, self-assemble themselves in an antiferromagnetic system below 10 Kelvin. Okay, so they are weak antiferromagnets. But when this group demonstrated was that when you grow these molecules on a surface of cobalt, for example, and what they observed was that you can exchange couple, obviously, and then you could see that you could create an antiferromagnetic chain, spin chain across the thickness of the MNPC molecule. And when they did smoke measurements, you could clearly see that as you cool down from room temperature, which is very symmetric, you start seeing an exchange bias. There's an asymmetry in the left and right. And this is an exchange bias shift towards the left. And what you observed was that when you reduce the thickness below the 10 monolayer, they actually are not able to observe any exchange bias in the system. And even otherwise, the exchange bias that they see are very weak. So the question that remained is, what is the origin of the exchange bias? So the claim here was that it is the interaction with the surface cobalt, which actually enhances the anisotropy, and also the spin change here gives rise to a more predominant strength, giving rise to exchange bias phenomena all the way up to around 100 or 70 to 80 Kelvin. And subsequently, there have been reports on many other systems of exchange bias, focusing on other material systems as well, whether it's cobalt PC with MOEP, porphyrin, or is it CSP. Of course, the mechanism is very different here, but most of the other studies have again have highlighted that the molecular spin change is playing a very critical role. And this is where I had a little thought process over the years in terms of trying to devise a measurement scheme that could help us identify what is the relevant role of interface here compared to the molecular spin chain, which is the source of antiferromagnetism. So with that in mind, we devised this project, which is we started using the same molecule, and we made two kinds of devices, both grown simultaneously in the same deposition run. And we used an in situ technique to be able to separate out the growth of molecule. So what we do is that we take the substrate silicon oxide, and we grow a layer of iron, okay? And we use a shadow mask to cover up the substrate for iron and grow the molecule on the other surface. And then we protect the surface with aluminum and capping layer, and we do standard capping layer techniques to grow these devices. Okay, and so the main goal is to be able to understand our interface effect. So that's why we limited the growth of the molecule to less than 4 monolayers. Okay, we never went about n monolayers. I mean, trying to replicate the other data. And this is data on the capping layer. I mean, the capping layer is fully covered, and then we have very good control on various stacking of these surfaces, interfaces. And this is just a slide that I had to tell you that the capping layer of our aluminum is very uniform, and then we can actually induce even superconductivity in just 5 nanometers of this aluminum. Talking about the very nice coverage that we can achieve in our growth system. Okay, so now let's come to the results. So first result is room temperature, MOC, and AMR studies. So what you observe here is essentially two charts. One is for 3 nanometer study using MOC and AMR, and other is for 5 nanometer. You can see for 3 nanometer, you can see for the reference ion, which is a blue curve, the coercivity is small, which gets enhanced in the red curve with the molecule on top. And the same is true for AMR. But as you increase the thickness of 5 nanometer, you hardly notice any change. So to sum up, you basically see a response like this, where at thicknesses above 5 nanometer of ion, it's mostly the bulk effect that dominates your signal, switching signal, and therefore you're not able to see any interface effect at room temperature. And even when you go down in thickness below 2 nanometer, you are essentially ending up into a super paramagnetic limit. So your resolution in terms of magnetic hardening is not clearly visible. So it is this thickness regime of between 2.5 to 4.5 nanometers that is quite interesting. And we retained essentially most of our studies in this region. And then started doing low temperature measurements. So now what you see is the AMR measurements that was done as a function of temperature. And this is summed up here. What you can essentially see is enhancement in the coercivity of your system. And this is again a systematic study that has not been done before, which is we looked at how the coercivity evolves for a reference ion, which has grown the same deposition run. Okay, compare it with MnPC on ion, and also we have tried cobalt PC. What you see is that related to reference ion, the coercivity enhancement is stronger and picks up at below 100 Kelvin. And this is again understandable from the interface chemistry, because if you see here, when a molecule, MnPC, sits on a surface of ion, it is actually bonding to almost around 20 ion atoms underneath. And if you talk about thermal energy per bond, which is around of the order of thermal activation, which is KT, okay, thermal fluctuations. So it's around KT. So you can talk about the actual thermal excitation that this bond faces is 20 times KT. It's almost of the order of 0.6 electron volt, which is quite large. Okay, so so therefore at room temperature, the interactions are weak and get stronger and stronger as you cool down. And that's one of the reasons why the hybridization effects become stronger, giving rise to a larger enhancement in the coercivity of the system. Okay, so this is something that we have observed. Now we cool down the system to base temperature, which is 1.5 Kelvin, and we did AMR measurements as with increasing field range. We started with 200 royston, we see no hysteresis, no hysteresis, no hysteresis. At 700 and above is where you start seeing hysteresis. So what we are seeing is this phenomenon, what is called the exchange spring effect, where you have a combination of hard-soft layer, where the hardness is coming from the surface molecular interaction, and your soft layer. And you are seeing a spring action without any hysteresis up to a certain critical field range. And it's only once you break, irreversibly break this coupling partially, that you give rise to this exchange bias. You can see that now 0 is here, and you have an exchange bias here that appears in the system. So we've done these measurements even on cobalt PC in both 0 field cooled and field cooled. So we've done these measurements in 0 Tesla, which is a blue curve, and 0.3 Tesla, which is a red curve. So obviously when you cool down in field, you see a stronger asymmetry in the AMR response. But most interestingly, the 0 field data is also very robust. Even in cool down in 0 field, you are seeing strong exchange bias. In fact, therefore it made us believe that it is the residual remnant magnetization of the bottom ion layer that is already strong enough to give you an exchange bias system in these systems. And more strikingly, we're not talking about 4 monolayer, 3 monolayer, we're talking about just a single monolayer coverage of the molecule. And even that shows a very robust exchange bias effect. And this is what I've shown here in this right plot in the training effect. So what we have done here is we have measured AMR multiple times, and within a training field of around 0.2 Tesla. Okay, and we have, for every AMR cycle, we have extracted the value of exchange and the coercivity. which is shown here. You can see after 9 cycles, they actually really flatten out to around 50 millitesla, which is also a very large value for the exchange field. And the coercivity also kind of flattens out. Okay, so this is an interesting aspect where this is one of the first times where we are seeing a robust exchange bias, which is stable, it's retained, and I'll come to the robustness in the next slide. But the question is, what is really happening? What is the source of this exchange bias in a monolayer system? Okay, so that's what we are talking about here, where you have a surface which is coupling with the molecule. Okay, of course, this is not 1.5 nanometer. For monolayers, it's around 0.4, 0.5 nanometers. But you are creating a surface layer which is interacting with the molecule and creating a very hard surface, magnetically hard, with a very large coercivity. And the bottom ion layer flips relatively left to right, giving rise to an exchange bias phenomena originating from this coupling, which is breaking the coupling between the surface and the bulk. Okay. Now let's talk about the robustness of the system. So this one way to check is, we have again repeated the training measurements, but with a training field of 0.2 Tesla at each data point. Okay, but at this 5th cycle onwards, we started applying a one-sided destabilizing field, which ideally should kill the exchange bias, and we progressively increase. So you apply 1 Tesla, and then you measure and you report the values. Then you measure, then you increase this field 2 Tesla in one direction, and you will start. And what you see is that you're actually killing the exchange bias stronger. And so we have gone all the way up to 7 Tesla. And then we stopped applying this one-sided exchange bias and did our normal training cycle measurements. And you can see a healing effect. You can see the exchange bias picks up and again saturates. So this is again a very clear indication of how robust this exchange bias is in these monolayer systems. Okay, so to sum up, so what I'm showing in these two plots is lots of data, but the focus is on let's focus on the one monolayer systems only. Okay, so I'm plotting the exchange values and I'm plotting coercivity values as function of temperature. For the case of cobalt PC, you start seeing exchange bias below 50 Kelvin. Okay, that's the place where the red curve starts picking up. And for the case of MnPC, the exchange bias onset happens at around 30 Kelvin, which is shown by this blue line. Now, if you see here, when you try to measure the coercivity of the system, it increases almost sublinearly, almost picking up rapidly up. But as soon as you start seeing exchange bias, you observe a plateau-like response. The coercivity just evens out and flattens out essentially, right? So this is something very interesting, because what is really happening here is this phenomena of this monolithic Crane-Pulley effect, which I personally say is not just because of surface magnetic hardening. There are two effects that is contributing to this monolithic Crane-Pulley effect. One is you have surface magnetic hardening, which enhances or stabilizes the surface. And the second is the hybridization-induced changes in the intra-interlayer exchange between the bottom ion layer, which is away from the interface, but it's enough to be able to modify the exchange strength within the bottom ion layer. And this is what I've shown schematically here. Okay, so if you start with, say, a reference ion sample, which is shown by the HC bulk, its coercivity increases gradually with temperature cool down. Now, if you compare just the coercivity of the surface, a hypothetical or a phenomenological system where you have just considered the surface with its coercivity as a switching field, you can see a switching field is here, and as cool down, it really goes up, shoots up, and really crosses almost exceeding 7 Tesla, I would say. Okay, it's very large. And now you look at your measurement that you're doing. You're actually measuring the whole system. You're measuring the whole system here. So when you cool down, your coercivity increases. At the onset of exchange bias, it's only the bottom ion layer that switches. And you're measuring the coercivity of only the bottom ion layer, which shows only a gradual increase in the system. Whereas the surface just is magnetically hard, and you start seeing a decoupling effect in this interface. So this is more in detail, which I would recommend you to have a look at this article. But the concept being that this is the point at which the surface magnetism becomes energetically favorable to be acting like an independent system and allow the bottom ion layer to switch independently from the surface. So how do you model this exchange bias? Okay, so that comes with theoretical modeling. So what we have done is that we have obviously taken the fact that we have an exchange bias, And this is typically modeled, one of the way to model this is in terms of using Stoner's criteria. So Stoner's model for Ferramanism. Okay, Stoner-Wipfer model. So we take this model where we have the device here, okay, and we are measuring the AMR as a function of angle between this current and the applied field. Okay, so we are rotating a sample in plane, and this in plane rotation is done by this phi value, which is what we have shown here in your right inside. So we have one molar device, we have an AMR at 0 phi, where it's very symmetric in the sense the left and the right, they both saturate at the same resistance value. As you create an angle phi of around 30, 60, 90, what you see is 30, you see asymmetric response. But with the shift, there's delta R shift compared to the left saturation value and right saturation value. Okay, and this delta R again is here, and finally it becomes 0 at 90. Okay, so how do we model this system? So you model this system by actually assuming, for example, if I give you this plus has to be a molecule, say we know that this MNPC has a four-fold symmetry, right? This has a four-fold symmetry. So I've denoted this by a plus sign. And we know this molecule typically sits on an ion surface in a random orientation, which is shown by this random orientation of this plus. And if we say that this molecule is inducing anisotropy, which is evident because the cohesivity, you are creating a surface magnetic hardening, which is evident even in this class, where the cohesivity of the bottom ion layer is much larger than the reference ion layer still. So you are inducing an anisotropy in the bottom ion layer because of this surface interaction, which is denoted by this K exchange induced. So this K exchange induced, so I have given it an axis of this molecule, which is randomly positioned. And so we have taken a model which can take into account all these complexities, and you can average this AMR effect over this random orientation of this molecule. And what you see here, the pink lines, is the fitting at different values of phi with all the parameters being the same. And this is reasonable fitting because we haven't really induced standard deviation of the cohesivity and all those things, but it's a very reasonable fitting, giving very nicely all the important specific trends in terms of how saturation happens in the positive and negative field. So what we have essentially, I've just given you an expression here, but I would recommend you to read our paper. But we have a Stoner-Wipfer model, which the first term here is the unidirectional anisotropy, which is an indicator of the exchange bias effect. And then you have the HBA, which I will come into later. But this is this is essentially related to this induced anisotropy because of the interface hybridization. And this can be modeled by taking, all kinds of possibilities, whether it's biaxial, uniaxial, threefold, fivefold, sixfold. You can just put in various parameters here. Obviously, the parameters here will change, and you can try to fit your data. So what we have done is that we have taken this delta R, okay, this delta R value, and we have measured this delta R as a function of this phi, as a function of the rotation, in-plane rotation of your system. And we see a four-fold symmetry. Okay, this is a very interesting result where we see a four-fold symmetry. And this, actually, if you put in a biaxial term, which is why you have this four term here, if you take a biaxial anisotropy, we're able to perfectly fit all these things and also show the four-fold symmetry of delta R. So this really signifies that we are actually seeing a four-fold symmetry being induced in this bottom ion layer. And just to give you perspective of the origin of delta R, this is simply happening because if I tell you this is the four-fold anisotropy of the interface of the bottom ion layer, and you have a unidirectional anisotropy created by field cooling, or for example internal anisotropy giving rise to a specific orientation of the unidirectional anisotropy. Now, when you apply field from top to bottom, okay, let's say you're talking about the cyan color. So you rotate your magnetization like this. And once you go back in field, it prefers to go back in this direction because of this additional term acting on the right section of the system. But things can change when you rotate your system. When you rotate your system, it can come back this way, but instead of going back the same way, the magnetization can rotate a full 360 degree. So you're talking about rotation pathways that is different depending on the value of phi. And this is specifically the reason why that gives rise to such an anisotropy or this angle dependent response. And it confirms, these fittings confirm that we actually have a biaxial anisotropy in the system. Okay, and this is somewhat very surprising, unexpected, because first of all, we are dealing with iron, which is just around 4 nanometer thickness, and grown on silicon oxide, sometimes on aluminum. So you're not expecting it to be epitaxial in nature. They are polycrystalline to the best that we can, of course, 4 nanometers is very difficult to detect from study as well. But these are polycrystalline, tending towards polycrystalline nature of the system. So, and it's very well known. You just can't see 4-4 symmetry in iron in this case. So the question is, what is the origin of this biaxial? And that's an open question in this community now that after our result, which is, we believe strongly it has to do with the pi-d hybridization effect being induced in the system. And now the question is, what is the role of molecular symmetry? Because is it just a coincidence that the molecule is 4-fold symmetric? And is this 4-fold symmetry that is replicating in the electronic density of states of the interface and therefore giving rise to a biaxial anisotropy? And does that mean, therefore, that if you perhaps have a molecule which has different molecular symmetry, then can they induce different kind of anisotropies? So that is an open question that I thought I will leave this discussion with an open debate, which is will be an interesting thing to follow up and look at interactions at these systems. So with this, I would like to conclude essentially by saying that what we have reported is a very robust exchange bias, and it's one of the most robust that has been reported so far. In fact, in the molecular exchange bias system with a biaxial anisotropy. And since we're seeing this in a monolayer system where we don't need any antiferromagnet by itself, so therefore this is, I call this as a 2D exchange bias effect, where we don't need to, there is no scalability issues. And this can essentially help us in terms of designing exchange bias systems at 2D levels. Okay, so that's one of the advantages of this work. And obviously from a physics point of view, we have been demonstrating this effect, which we call as a Crane-Pulley effect, signifying essentially that you can actually indeed decouple the surface of a ferromagnet from the bulk of the ferromagnet, which earlier was never anticipated one could do. You could at best weaken the ferromagnetism, but being able to decouple completely and allow one to switch independently of the other, of course, through an exchange bias mechanism, has been one of the work that we have right now shown with these systems. And I hope that there will be more work coming in, especially in these systems, not limited to tyrosine molecules, but other molecules also. So with this, I would just end. And since I have just a minute, I can also talk about some of the ongoing works that we are trying to also work on, which is reporting this unexpected spin glass response. And what you see here is essentially a similar study that we have done for these systems, except that now you can see that, say in this system, you can see that instead of coercivity increasing, you can see that for a specific cool down procedure, you can make this coercivity to go down. And this is one of the indicators of a spin glass response, because you no longer see an exchange bias. The exchange bias is completely killed in these systems, shown as purple line. Okay, so this is a spin frustration system that we are trying to understand, but it's very unexpected because first of all, even though in zero field cool you show a strong exchange bias, you need to essentially cool down in oscillating field to be able to create this. And what so far our understanding is that we still retain the strong exchange bias across the interface, even though you experimentally observe zero exchange. But when you do angle-dependent study, we observe that the exchange anisotropy is as strong as what you observe in zero field cooled or field cooled studies. But what is causing this spin frustration response is within the bulk of the ion, bottom ion. So there are more studies awaited, but this is what I had so far. And with this, I would like to conclude, and I think I would be eager to take any questions in the next few minutes that we have.
Okay, thank you so much, Karthik. Braj is here. We both clap for you. Your excellent lecture. So there are a couple of questions already in the chat window, but I would like to ask one question before I forget it. So how did you measure this exchange bias, by the way?
So this exchange bias is just measured from the AMR study, and in terms of denoting the position of the, one second, just go back.
So did you make any field cooling from high temperature to the measurement temperature or something like that?
Yeah, so we have cooled down various fields. I think I had the data somewhere, one second. Yeah, so, okay, so let me focus here first. So we have cooled down in 0 field, which is blue curve. Okay, and 0.3 Tesla. So we have cooled down various fields, and what you see is this plot here. This is, you can see the exchange value is independent of the field cooling procedure. There's hardly any change in the exchange.
Okay.
Okay, they're almost independent, which is what is surprising. And this tells you that actually the remnant magnetization within the bottom ion layer is enough to induce a strong exchange at the surface with the molecule.
No, I'm sorry, I didn't get. So this insert is basically for which sample?
This is for MNPC. This is for ion MNPC sample, I think, yeah.
So you are telling when, but that shows that when you do this field cooling, so it doesn't really depend on the cooling field magnitude, yeah?
Yes.
But in one of your plot, where you are showing this trending effect.
Yeah, no, this is field cooled. This is field cooled value.
Yeah.
The other one is the training effect. Training effect.
Yeah, this one.
This one or next one?
No,
this
the next one.
Next one. This one?
Yeah. So here also I didn't get. Then what is this 1 Tesla, 2 Tesla, 7 Tesla?
Yeah. So basically, you know, when you create an exchange bias, the hard layer, the magnetic layer is pinned in one direction, right?
Yeah.
So what I'm doing here in say cycle 5 is if I say, for example, the exchange is pinned, the surface is pinned in the right direction. Okay, the right spin is pointing of the hard layer is pointing right direction. I apply a 1 Tesla field in the left direction, bring back the field to 0, and then I measure the AMR with a training field of plus minus 0.2 Tesla.
Okay.
And then I measure the value of exchange and coercivity, extract it from the AMR plot, and show you the data. Then I apply next cycle, just before I measure again the AMR, I apply minus 2 Tesla, one-sided, minus 2, which is opposite, in the opposite direction to the hard axis. Okay, so that I try to break this exchange bias. So I apply 2 Tesla, and I again repeat it. Then the next step, I apply 3 Tesla, and even up to 7 Tesla, you know, I'm bringing it down. So you can see it's a faster ramp down.
Yeah.
But after this, I'm no longer applying any high one-sided field. I'm back to normal AMR measurements within 0.2 Tesla, plus minus 0.2 Tesla. So there is a healing process, a recovery process that happens. Basically, this is like a spin glass. We are kind of breaking it. That's why the coercivity is going up.
So just last question from my side. So if you do not do this, this is kind of minor loop with an perturbing field, then do you get just exponential decay of the exchange bias as a function of the training cycle?
Yeah, I think if I keep it at 7 Tesla, maybe I haven't tried it, but it's just because of time. But if I apply 7 Tesla all the time, one-sided, at some point it could probably just saturate and not go to 0. Okay. My feeling is it's so robust that it doesn't go actually to 0. It just stays down.
Fine, thank you. Okay, before I put more questions, so I think Mahendran has a couple of questions.
I'm looking at the chat box.
Feel free.
So the question is it the terbium polarized by cobalt iridium? So
thanks. It's a terbium. I'm asking terbium band. First of all, sorry, I congratulate you. The talk is very interesting.
Thank you.
The results are certainly interesting. So my question is the terbium band polarizer in the first compounds you have described? I think, yeah, this one, terbium, I don't know what is PC2, I don't know what is that.
Calcium, yeah. So India, what is the question? So iridium is
the question is that is the terbium band polarized by this cobalt iridium?
So this is so first of all, terbium is in a Ligan framework. It's in a Ligan field of the molecules. So therefore, it's is not really a band of terbium, but yeah, you can talk in terms of the terbium states, electronic state. You are essentially looking at the electronic states of the molecule as such by the tip. Okay, and so you are looking at these states, which is a combination of terbium band, terbium electronic levels coupled to the molecular levels, hybridizing together to creating molecular states. And it's these molecular states that you're probing with the STM on top.
And what temperature this measurement was done?
So this measurement was done at, I think, 4.2 Kelvin.
I see. Okay. I think the other questions are related. Now probably understand. I asked the questions why you measure AMR instead of longitudinal MR. I mean, after your talk, I understand that probably you are trying to see the symmetry of the molecule on the surface. Is that the reason?
Sorry, longitudinal MR and AMR is essentially the same thing. Sorry, so it's a longitudinal MR only in plane. Sorry. So yeah, the field is in plane only.
Oh, field is in plane, but still, are you doing the angle dependence?
Yeah. Okay. So angle dependence is essentially in plane field is rotated with respect to with respect to current direction. Yeah. So the current it's a long strip, and the field is rotating in plane.
Okay, then I got the point. Yeah. Thanks very much.
Thank you.
So the next question is by Sobik. Please ask your question.
Hi, Karthik. Am I audible?
Yeah, you are.
Okay. Yeah, great talk. It's Shobik here. So I have a couple of questions, if I'm allowed. So it's very interesting. So first thing is, if you want to have a enhanced this exchange bias effect, how do I choose the molecule? It was not clear to me that what kind of properties am I looking for the molecule itself? Is just I have an empty pi orbital?
Very good.
Yeah. So this is something was not clear, especially in the earlier days, and still to some extent it needs input from theoretical work. But the main thing that is required, as I see, is the strong. So this is something a priori it's very difficult to ascertain, but you can talk about classes of molecules that can show. For example, class of all thermocyclic molecules, I would say, are showing it because they hybridize strongly with the surface. And this hybridization is governed by the molecular symmetry because they are planar aromatic. You have pi orbitals, pi bands, which are strongly coupling with essentially, for example, the pz orbitals or p bands, or the d bands of the transition metal surface. And this exchange bias, as I said, has two key ingredients. I mean, people have seen surface magnetic hardening in many reports. Sorry, let me just go forward. They have seen surface magnetic hardening in many reports, which I had shown here. And there are many papers after 2010, 2011 that people have started seeing and appreciating that, yes, there is indeed surface magnetic hardening is a real concept. But to people to see exchange bias, which is what I have been thinking about for a long time, which is there are two factors. Surface magnetic is one thing, but the other aspect is that you can actually also play or strongly modify the intra-interlayer exchange coupling, magnetic exchange coupling across the surface, across interface. In fact, DFT has also confirmed that when you have this hybridization of this, say, molecule with the surface, the interlayer exchange between the surface and the bulk can go down by almost 90%. Okay, the exchange coupling strength. So typically it's around 8 milli-electron volt per cobalt atom in bulk. For cobalt per atom, it can go down to almost 1 milli-electron volt. So it's a factor of 1 by 8 that is dropped. So what we're looking for to be able to see exchange bias is primarily if computationally, if suppose some molecule shows you that you can enhance spin orbit effects at the surface by that interaction of the interface states. And secondly, if you're able to demonstrate from DFT or from computational studies that the interlayer exchange strength
Right.
by essentially doing spin polarized non-collinear DFT calculations, you can actually show that if the interlayer exchange coupling between the surface and the layer below it is actually reducing drastically, then this is a very good indication that that molecule will show exchange bias.
I see. Okay. Okay. So I had a related question. I mean, so still, so you know, in this this PC molecules, and I have no idea about the band structure of these molecules per se. So how does it change from when you go to manganese to cobalt? Because your response was quite different. And the second was that, so you said that you know, like you explained with the Stoner criteria. Is there any experimental evidence of that it's really like a Stoner-like? Because I was a priori thinking there could be some local moment behavior, you know, like because of these manganese and cobalt molecules.
Yeah, in terms of Stoner, I'm sorry, in terms of Stoner criteria, I mean, that's one of the models, theoretical predictions being putted, but this is also the fact is that this study was done on, one second, where is that study? Yeah, the study was done, I think this copper was, copper is not really epitaxial, or these are again kind of very thin, smooth films of copper that are grown.
Mm-hmm.
Okay, so they are again having defects, but there is no band structure evidence from experiments using RPS or something. But there are related works where using RPS spin resolved techniques, people have shown when you put the molecule, you can actually invert spin polarization. You can induce, I think there is a report also on inducing magnetism. I'm not sure of copper specifically, but there are reports of other transition metal surfaces, non-magnetic, where you put the molecule, you can actually induce ferromagnetism.
Okay. And about the like cobalt to manganese, I was just wondering, like, if you have any idea, like, how is the electronic structure getting changed in the molecule itself? Is it just the I don't know, the local activity of the orbitals, or
how is the molecule states changing, you mean?
Yeah. I mean, when you go from, so is it just that the molecular orbital picture that is important, all that I need to care about to understand the change?
No, so molecular orbital picture actually fails down.
Mm-hmm.
Because see, you molecular orbital theory to some extent is good enough in these systems where you have discrete energy level.
Right.
But when you hybridize these discrete energy levels with a band, you end up into you can say it's acting like, that's how I showed my schematic. You talk about in terms of bonding and anti-bonding bands, which again might rehybridize, and you could give rise to very different electronic states. And I think, I should have plotted, I should have shown it, but I haven't. Yeah, this one. For example, this plot here, what you see here, this red one, right? Red and blue.
Mm-hmm. Yeah.
This actually, I have not shown above the formula, but it continues. Okay, so this is the state, this is the electronic states of the molecule, not of the ferromagnet.
Yeah.
So the molecule really hybridizes strongly. It becomes a metal.
Mm-hmm. Okay. So so my question more was like, when are you going from cobalt PC to manganese PC? Like, what mainly is actually changing in the, because your response was quite different, I thought. Like,
so typically what is changing is that the spin density also gets affected, because cobalt being cobalt, it has a higher spin density compared to manganese. So that affects the contribution of both the ligand and the central metal atom. So that effectively changes the interaction strength, the spin contrast across the interface, and effectively gives rise to different strength of hybridization.
Okay. And if I may, I had a quick last question. Is, so how do you grow these molecules? Like, is it?
Yeah, these molecules are stably thermally evaporated in an MB system. They
okay, so it's like an effusion cell kind of a thing.
Yeah, like yes, effusion cell, around 500, 600.
Okay. And is there possible, like, do the self-assemble, like if you grow, like do they have any terms, any?
Yeah, so self-assembly is possible on inert surfaces very easily. They self-assemble easily on gold, inert surfaces, platinum. Okay, because there the molecular interaction is dominant over the molecular surface interaction.
Okay.
So when the molecular interaction is dominant, they self-assemble.
I see. But if you have like the first layer covered, then you can't keep on self-assembling even on, like, let's say copper or iron?
No, on copper also they self-assemble, and gold, iron is difficult, yeah.
Okay, thank you, yeah.
Okay, if I may just add to one of the question which Souvik asked you. So on this copper C60, so I think there is a little bit of debate in the community. Some people try to reproduce, and they told, at least I have discussed with a few people, this Ileana Borgenti from Italy. So they could not reproduce, but in our group we have prepared this copper C60, and it's very interesting that only at this small thickness, about 2 nanometer, so you get the ferromagnetism in copper, and we have even performed the eccentricity, and we could see the ferromagnetism in copper. A manuscript is under review. So, but it's very interesting why only like 2 nanometer only gives ferromagnetism and not thicker or not thinner. So this is something to be really understood, and definitely something to do with the band structure modification probably.
Yeah. So as you go make it thicker, the bulk bands dominate, and bulk bands don't let you approach the Stoner's criteria. In fact, that was one of the debates, that if that is the case, then materials, I think platinum is somewhat which is the most closer to Stoner's integral, exchange integral.
Yeah.
0.8 or 0.9.
Even if you go below like 1.5 nanometer, then also you don't get it.
Yeah.
So if you just saw that slide, it has a clear Gaussian shape. So yeah. So it's not really. It is happening just around that thickness. That's something to be understood in future. And just one comment before I go to the next question. In the literature survey, I think one of the first slides regarding this change in anisotropy. Here. The next slide, where several references are cited. You have cited very kindly one paper from my group, but actually in that paper we have not shown that it is switching from in plane to out of plane. Rather, we have shown that
that is for the first paper. Yeah, sorry.
Yeah, Boiragi paper and other paper is fine, but our paper has shown that it is always in plane. But when you deposit C60, it is actually enhancing the anisotropy.
Correct.
Yeah. Just a small thing.
No, I agree. I just haven't put titles for all of them as well.
Yeah.
But
thank you so much for
only on 360 work, that's all.
Always like that. Appu Kumar Jana, please ask your question, or should I read it? Okay, I will read his question.
What is the equation of the unidirectional anisotropic constant which you have plotted as polar plots? What is the equation? You mean?
I think he's talking about that anisotropy fitting, and where you have axial here.
You can ask can I ask my question?
No,
okay.
that is Jyoti. That is
okay, sorry. So Stoner-Woolford model. Are you talking about Stoner-Woolford model?
Yeah, I think so.
Or you're talking about something different, especially what is HUD only. So the Stoner-Woolford model essentially comes assuming essentially a single domain physics, where you talk about this single domain having its internal anisotropy, which is given by this term here. In this case, it's biaxial energy because of the biaxial term, and then this is the energy because of applied field. Okay, HA cos theta, and this term is arising because this domain is exchange coupled to something which is, say, antiferromagnet in a typical case. Okay, so that introduces an interfacial anisotropy that gives rise to exchange bias. So this term is just an exchange bias term, represents the exchange bias term. I hope I answered your question. But you could easily look at references on Stoner-Woolford model. It's a standard textbook physics that you will find at many.
Yes. Jyoti Mohanty, please ask your question.
Can't hear you, Jyoti ji.
Yeah, Jyoti, I cannot hear you. Okay, maybe he can type his question, and in the meantime, ask another question.
There is one more. Are there any molecules where the effect you have shown observed at room temperature? The surface hardening effect is observed at room temperature also in C60 molecules. So surface magnetic hardening has been observed in many papers. Other effects, exchange
like the AMR.
Like the AMR. So AMR is somewhat unique because, so far people have been focusing on making device. That's one of the things that we focus on AMR is because most of the time people make devices, TMR stack, GMR stack, and it hasn't been clear, people have always been questioning about whether molecule is getting punctured by the top electrode, creating filamentary channels, and what is the role of these filamentary channels in terms of its magnetization response. So to keep things clean, that's why we have used AMR technique. So far, there hasn't been much AMR work on molecule stuff. It has been used in typically ferromagnetic and antiferromagnetic systems where they have done angle-dependent studies and observed these effects, but nothing so far in the molecule system.
But nothing at room temperature also so far, is it?
And the room temperature also so far. Exchange bias, no.
I see. Okay, thank you.
So therefore, the question is, if you choose the right molecule which has the right interface chemistry, perhaps one could enhance this effect. So far, people have been observed these effects up to around, I think, 100 Kelvin. But it's a matter of finding the right molecule.
Yeah.
Oh, okay, thank you.
Yes. So I think we have to now wrap up. So thank you everyone for joining. Unfortunately, we could not take the question from Jyoti, some issues, and he also has not written it.
Yeah, Jyoti, give me a call.
Okay. So we will discuss that later. I have to also hurry up for another meeting. So thank you so much, Karthik. And we will be in touch. And thank you everyone. See you next week. Next week the talk will be at 6:30 p.m. not 4:30. Thank you so much. Take care. Stay safe. Bye bye.
Who is the speaker next week?
Next week I think it is. I also forgot.
Okay. Okay. We'll wait first.
I will tell you one. I think you are on.
29th.
Maybe it is you.
Next week, not me. 29th, I think.
Okay. Okay. So then next week I will let you know. I forgot. Okay.
Okay. Fine.
Yeah. Thank you.
Okay.
Bye bye.
Okay. Bye bye. So I remind you about the